Hey folks, welcome to Chapter 8, Section 2, Graphing Rational Functions. In this video, we're going to look at rational functions. Those are your basically your inverse functions if you were to relate it back to 8.1. And so we're going to talk about like the domain and range of those functions and the asymptotes of those functions. So let's go over some definitions up at the top. The graph of the parent function is, for a rational function, f of x equals 1 over x, where x can't equal 0. Why can x can't equal 0? Why can x not equal 0? Because you can't divide by 0. There's no multiplicative inverse of that. So x can't equal 0. So because x can't equal 0, you have these two asymptotes, these imaginary lines, and when it's just 1 over x, it's the x and the y axis. So if x can't equal 0, there's an imaginary line splitting the graph right there. And since x can't equal 0, y can't equal 0, so there's an imaginary line splitting the graph right there. So the, what, oh, I was reading this, the inverse variation function, I already said that. So the graph of a rational function is called a hyperbola, so that's what this graph is called. And the domain is all real numbers where x can't equal 0, and the range is all real numbers where y can't equal 0 because of those asymptotes that I just talked about. So any function in the form of g of x equals a over x where a can't equal 0, so you can't have 0 on top because then it would just make everything go to 0. That's why it just says 0 can equal a can equal 0, has the same asymptotes domain and range as the parent function 1 over x. All I'm trying to say is change this number to 1, -3, 10, 20 billion. As long as it's just divided by an x on the bottom, it'll have the same asymptotes where x can't equal 0 and y can't equal 0. That's all I'm trying to say. Look at this graph right here. We have a graph of 4 over x and 1 over x. The 1 over x is in blue, and 4 over x is in red. So we're just going to talk about the differences and the similarities. So basically the main difference here is that g of x is lying farther away from the x and y axis, or axes, than the graph of f of x. But other than that, everything else is ultimately the same, okay? So that's all I'm going to say for the differences. So that's basically how I wrote it down. The graph G lies farther from the axes than the graph of F. So what do they have in common? Pretty much everything I just introduced to you in the definitions, meaning they have the same asymptotes. That's the biggest thing. So if they have the same asymptotes, then they have the same domain and range. And then just for the sake of it, they're in the same quadrants. If you recall your quadrants, the quadrants go 1, 2, 3, and 4. So they're both in quadrants 1 and 3. So there you have it. That's what I officially wrote down. They have the same asymptotes, domain and range, and both graphs are in the same quadrants. All right. So next we'll talk about translating them up, down, left, or right. So I want you to follow these steps to identify your asymptotes, domain, and range for a rational function. So if you move it up, down, left, or right, you're going to be adding or subtracting something on the bottom or adding or subtracting something on the side, okay? So adding or subtracting something on the side, aka the outside, moves it up or down. Those are things we've gone over in the past. And adding or subtracting things on the inside, that's part of the fraction, is moving it left or right. And so you remember, if you minus a number, it makes it go right. If you add a number, it makes it go left, okay? And so it's just denoted here in this little formula with h and k. Kind of like that of the h and k that's in the vertex form of a quadratic function. So here we have the vertical asymptote is always at x equals h. If it's just x plus a number or x minus a number, yeah, it'll be at x equals h. Just remember to like flip that sign basically. The horizontal asymptote is at y equals k. So whatever the number is on the outside, just put that number. And then so the domain is always all real numbers where x can't equal h. And the range is all real numbers where y can't equal k. All right, so here is my first example. Let's identify what the vertical asymptotes are at. So here we have x plus 2. So your vertical asymptote is always x equals. See, I mean, I said it and I read it, but I just want to highlight it some more. Vertical asymptote is always x equals. So it said x equals h, and the formula was minus h. So I just want you to say x equals, flip the sign, -2. Remember, we flip the sign on the inside. That's kind of like the pattern we've gone over. The horizontal asymptote is always y equals. All right, so y equals, and then it doesn't flip the sign on the outside, -1. The reason why you flip the sign is because you want this to be equal to 0, okay? So like you're basically setting that equal to 0. -2 plus 2 equals 0, because we can't divide by 0, so we need to figure out what number will make it go to 0. That's basically it. And so the number on the outside, there's really nothing to it. It's just if this can't become 0, then this number will never happen. That's why you just write this number down exactly as it is. So now that we've identified our asymptotes, identifying your domain and range is real simple. So your domain is, you can say it two different ways. You can say all real numbers such that x can't equal whatever the asymptote number is. You'll also see it written as, remember this form, x such that, that line stands for such that x can't equal -2. Either are okay with me. I just want you to know, like, you know, what you might see come test time. So my range will be all real numbers such that y can't equal -1, or you say y such that y can't equal -1. They're saying the same thing. Just want to show you the different ways. I'll probably, just because I think this is what you're more likely to see on the test, I'll just continue doing this. But who, you know, I so often write it like that, I might end up just doing that without even realizing it. So I'll just try and make an effort to do that. But yeah, that's all I have to say about number 1. Number 2, we have a -2 on top. That doesn't really affect our asymptote that exists on the bottom. So x minus 1, if you were to set that equal to 0, you'd have a vertical asymptote at +1, x equals +1, or just 1. So you're flipping that sign. And so your horizontal asymptote is just y equals 3, okay? So at this point, you might be asking, why is x vertical when x goes left and right, and why is y horizontal when y goes up and down? So for that, I say, let's look at a graph. So you can see on the graph that anytime you graph an x equals equation, it's going to make a vertical line, because think about it, x is a horizontal line, the x-axis, and so if I were to try and cut through it, the only way I'd be doing that is with a vertical line. So x equals 1 is a vertical line, and then the opposite's true for the y-axis. The y-axis, yes, that's vertical, but if you're going to cut into it, you need a horizontal line. So y equals 3. And so I highlighted the intersection between your vertical and horizontal asymptotes just as something to point out, just because it's kind of neat. But so you know how we have the h and k here, and then you know, in your vertex form for a quadratic formula, the vertex is at hk. So it's not like super essential or anything, but your asymptotes do meet at that h comma k, and I just think that's interesting, if nothing else. So with this information, let's identify the domain and the range. Simply put, it's just all real numbers such that you can't equal your asymptotes, right? So I'll write x such that x can't equal 1. So that tells me all real numbers, but x can't equal 1. And then my range, just look at your horizontal asymptote for what you can't equal. So my range is y is in all real numbers such that y can't equal +3. And that's it. So here on this example, I'm not adding or subtracting anything on the bottom, so my vertical asymptote is just simply x equals 0, okay? Because think about it, I'm not plussing or minusing anything, so you can't divide by 0, so x equals 0. So my horizontal asymptote is still just that number on the side, so y equals -2. We don't flip that sign or anything, we just copy it down exactly as it is. And so my domain will be x is in all real numbers, such that x cannot equal 0. My range is y is in all real numbers, such that y can equal -2. And that's all there is to say about that example. So j of x, I have a number on the bottom, so my vertical asymptote, set that equal to 0, x plus 4 equals 0, that means x equals -4. Now, there's not a number adding and subtracting on the side, so I don't want you to make the mistake of saying there is no horizontal asymptote. If there's a vertical asymptote, there's going to be a horizontal asymptote. So if there's nothing on the side, we'll just simply say y is equal to 0. And so my domain is x is in all real numbers, except x can equal -4. My range is y is in all real numbers, except y can equal 0. And so that's it for that. So for this last example, here I'm just kind of expanding on it, where I have my denominator, I have a number in front of the x. So I'm going to set that equal to 0 like I have been, except I'm going to write it down and show my work, just because it's not so obvious. Oh, just flip the sign. That's basically what we did on all the other ones. So here I need to add 3 to both sides, and I have -2x equals +3. So I'll divide by -2. And so I get x equals -3/2 for my vertical asymptote. So my horizontal asymptote, that remains unchanged. It's still just +5. So y equals +5. And so with that, I can write my domain and range statements. So my domain is x is in all real numbers, such that x can equal -3/2, and my y, or my range, I should say, is y is in all real numbers, such that y cannot equal +5. And so this last example is going to wrap it up for the notes. Thank you for watching. Stay tuned for an additional video over this section, and like and subscribe if you feel like it. Goodbye.